Well, hello everyone, and welcome to our Covering Environment seminar series. My name is Murat Kasira, and I'm a faculty member at the Biosystems Engineering Department and the Director of Controlled Environment Agriculture Center here at the University of Arizona. We have a fantastic speaker today, and I will be introducing him shortly to you. However, I would like to share some information with you about our upcoming events and encourage you to join us for these exciting events that are in front of us. So today we will continue our Covering Environment seminar series as we're hosting today our friend, Dr. Erico Mattos, and then we'll have Dr. Matt Lingard to present in our Covering Environment seminars in October. We are offering an intensive workshop on aquaponics with our instructor, Dr. Matthew Rexetar, in October. If you are interested in learning about aquaponics systems, designing an aquaponics system for your operations, if you're a hobbyist or if you're starting a business in aquaponics, we highly encourage you to register and participate in this intensive workshop in October. And then we encourage you to join us for our upcoming annual greenhouse engineering and crop production short course. We are going to have a hybrid event this coming March in 2022. We'll have some presence here in the classroom here at the Controlled Environment Agriculture Center with our exhibitor sponsors joining us. The seats are limited for this in-person participation here at the Controlled Environment Agriculture Center, but we also welcome you to join us virtually to this exciting event once again. So with that, let's get started with our webinar today. I would like to also acknowledge and thank Ellen Ward, our outreach specialist, and Dave Bogner, the director of our communications and cyber systems and technologies at the College of Agriculture, Life Sciences, as we together collaboratively offer these webinars and upcoming events. It is a pleasure for me to introduce and to you and welcome Dr. Erico Mattos for our Covering Environment seminar series today. Erico is a good friend and a colleague, and he is well known in the Controlled Environment Agriculture network and industry. Dr. Mattos is the executive director of the Greenhouse Lighting and Systems Engineering Consortium, and he is the co-founder and CEO of Candidus company. Erico earned his PhD degree in 2013 from University of Georgia and a BS degree from University of Sao Paulo in 2009. Erico completed Singularity University graduate studies program in Mountain View, California. Most recently, Erico was the recipient of the 40 Under 40 award by the LED magazine and recognized by the Produce Grower magazine back in 2019, and as a produce pioneer for his contributions to the controlled environment agriculture industry. At GLASE, the Greenhouse Lighting and Systems Engineering Consortium, Erico works with academics and industry stakeholders to facilitate the development and implementation of new technologies aimed to provide controlled environment agriculture, food production, sustainability. At Candidus company, Erico is the leading person in the development of and implementation of new lighting control technologies to increase greenhouses, lighting energy use efficiency, and maximize operations profitability. We're privileged to have you, Erico. Thank you for joining us, and the floor is yours.
Thank you so much, Murat. Thanks for the nice introduction. Thanks for inviting me today. Alan, thanks for organizing. And thanks everyone for joining us today. Happy Friday. Let me share my screen. And I think we can make sure that's not the wrong button. Can everybody see the right screen? All right, perfect. So thanks everyone. Again, thanks everyone for joining the webinar today. As Murat said, Since my graduation, I've been working in this intersection of academia and the private industry, both as an entrepreneur with my own company, and also now that I joined the GLASE consortium, I've been the executive director there for the past 4 years. So I thought it'd be nice to talk to this group today about those experiences, what I've learned, the challenges that I've seen related to how I can transfer new technologies that we develop in the lab into the industry. I have not been doing my own academic research since I graduated, but I've really been on this intersection. So I think it would be very nice to share some of these finds with everyone here today. And I'm going to be talking about advanced CEA lighting controls. Specifically, that's the area I've been working since I graduated, and also the area of my dissertation. So hopefully we can have a good discussion afterwards. Hopefully some of those questions and those points can help you now and during the future developments. So let's take a look. What my co-founder, I work with Mark Van Eersel, professor at the University of Georgia. One thing we ask all the time, working with directly with the industry, we ask ourselves why we're doing what we are doing, how we're helping growers. If we cannot say why is that important, we revisit and we try to arrange again. So related to that, I'm just gonna jump straight to the point here. What is the problem with lighting control systems in the greenhouse industry? The way we see, lighting is costing growers more than it should. And it's a simple thing. So there are many reasons why that happens, but it's just what it is. Lighting is the most important factor for plant growth, both in greenhouses and indoor farms. It is also the most expensive and the least controlled factor. And reasons for that is technology coming up now, going into the LED lighting systems. Those systems are becoming more accessible, they're more powerful, they can be integrated with many other systems, and that is relatively new development if you think about temperature control, irrigation control, nutrients control. So there was this lag in the industry between all the other systems and lighting, especially lighting controls. To give an idea, in 1 acre greenhouse, if you have 1,500 lamps or 400 watt HPS lamps, and you're running them 16 hours a day, running them 180 days a year, it will come to a cost of $90,000 per year. And that's considering the average price of 12 cents. That's the average energy price around the United States. And that represents 30% of the farm gate value of a traditional vegetable greenhouse in the United States. What is the problem? Why is that happening? It's because greenhouse lighting controls are not the most advanced today. There are 2 main controls out there. Many growers still use timers in which you're just setting the time on and off, and your lighting system is going to run throughout the day independent of what's happening outside. Or some growers can use threshold controls, and that is, to our knowledge, has been the most advanced type of control as of today, which is not really fancy, right? With threshold controls, you're going to be turning your lights on or off based on the external radiation. So you can measure how much sun is being provided to your plants, and based on fixed thresholds, the whole system is going to come up or off. And what happens, it just results in energy waste. You're going to be providing lights when plants are not needing them, sometimes of the year, and some other times of the year you might be under illuminating your lights because you don't have the dynamic control that your plants needs. And that's especially important if you see situations like that. This is a picture that I took about a month ago, visiting a farmer in Michigan, and was supposed to be a very bright week, but in the middle of the week, you get a day like that, in which 30 minutes of that can be everything clean, in 30 minutes of that can be everything dark, and your crops really get fluctuating lighting conditions, which will result in waste or underproduction. Now, that can become even more important if you think about that in this specific facility, they have in one of the greenhouses 2,400 LED lights. Well, 2,600, sorry. Just a quick math here. With those 2,600 fixtures, 600 watts per fixture, they have an installed capacity of 1,560 kilowatts running those lights 24 hours a day with no controllers at 12 cents a kilowatt hour. Energy costs for lighting only $2,250 a day. So around $67,000 per month. That is a significant cost if we're growing lettuce. The solution that we've developed and we've been using, right, we're implementing this solution not only through the company, but also that's one technology that has been developed at Cornell University, very similar for many years. It's an adaptive lighting control system. And the theory is not that complicated, it's simple. By monitoring the lighting conditions outside of the greenhouse and inside the greenhouse, we can determine how much light is being provided to the crops. And by doing that, you can control your supplemental lighting just by controlling the dimming of the LED lights. So you can provide very consistent daily light integral, day in and day out. So you're going to be pushing hard when you really need the light, but when you have excess of light coming from the sun, you can really nail down and save energy. A quick animation just show how the technology works. As you get a bright sunny day, lights will be off. You get some clouds, the lights will come at more power. As the clouds go away, your light's going to be dimming and regulating to find the right amount of light that you need at any time of the day. Pretty much what we're doing here, what is different from what is available out there, is that we're constantly measuring the amount of light. So those are variable thresholds. By knowing how much light your crops need in a certain amount of day, the photo period that the growers will choose, the system keeps integrating the lighting and will recalculate the amount of light to be provided at any time. And that can generate significant savings. To demonstrate what that does, we have developed a lighting cost estimator. It's a very nice tool that by using historical data, we can enter some of the specific information of the grower. So they will be providing the crop lighting requirements. They will be providing the lighting system specifications, the price of energy, and some other aspects of the production setup. After we have this information, we capture data available from historical weather data sets, and we can implement or we can impose 3 different lighting control strategies: an adaptive lighting control, a threshold control, and just by running the lights simply on and off timer. After that, you can immediately calculate your energy savings, and you can also see how many days you got to the target DLI, the daylight integral. And this is important because when you think about crop production, energy savings on its own is not necessarily what you're looking for. The joke that we have is that the most efficient lighting system is the one that you keep off. You're going to use $0 of energy, but then your crop's going to be very behind. So let's take a look on what that could be done in a location similar to Tucson. I look into the database that we have. The closest area that I could find was Las Cruces in New Mexico. It's kind of the same height as Tucson. And just by playing with that beforehand, I saw that doesn't make much sense to this location to provide supplemental lighting before November or after February. So I pick a given year. I was playing around. I think this one could illustrate well what happens. I took from November 2014 to February 2015, and I ran 2 scenarios. One in which a grower would have a supplemental lighting system capable of providing 210 micromoles of supplemental lighting at the canopy level, and another scenario where they could provide 110 micromoles per meter square per second. And those are arbitrary numbers to begin with. But after running a little bit, I saw that less than that would not be enough to achieve the grower's needs, and more than that just doesn't make sense to that location. What I'm showing here, I highlighted some of the inputs. We can go quickly the first time, but then you're going to be seeing the same scenario playing month over month with these 2 scenarios. What this tool allows us to do is a grower would set up the target DLI that he's looking for. So in this case, I had 17 moles of light per day. It's a very common target for lettuce. With the crop lighting capacity, that's where I set up for 210 micromoles, but they can also include some other information. A simple threshold, so we can run the threshold control scenario. In this case, if the sunlight is above 300 micromoles, the lights will shut off. If it's below the time, the lights will turn on. the fixture efficiency to run the scenario, and that's used then to calculate the costs. I set up at 2.2, which is similar to the DLC requirements today. I set up lighting transmission at the greenhouse at 70%. So then you can take that historical data and apply the transmission to have a good prediction of what will be inside the greenhouse. I set up the growing area for 1 acre, and the electric cost I set up at 10 cents. Up here, we can see the location that I selected. That was the closest one I had available. We're going to take a look at the month and the year. So I highlighted. We can keep seeing this changing. And I set up the photo period starting at 6 a.m. and then shutting off at 8 p.m. at night. So with the first scenario, what we can see here, running in November, in general, we have enough light coming from the sun. What this graphic is showing us is the first one here to the left is just the available sunlight that we had on that given month, that given year. The first scenario here, we have the imposed adaptive lighting control. If you can see the thin green line, that's the target DLI that is set up at 17. The scale is down to the left. The scenario in the center is the threshold control, where everything comes on if the lights are below 300 micromoles, or off if the sunlight's above 300 micromoles. And the last one to the right, more for comparison, I don't think everybody in theory would use this at this time of the year, is the timer control, where you just keep on to the entire photo period. But what you can see here is there is not much difference, right, between an adaptive lighting control and a simple threshold early on in the year for this case, for this location where you have enough sunlight. So here, not much savings, not much benefits, although we are really shaving on the top when you have enough sunlight because the lights are not being used, recalculating. But that's, again, is something that in practical meaning, I don't think people will be running at this month of the year. It's interesting here when you go to December. So now we have a month in which you have variable sunlight. Some of the days you are achieving your target DLI, some of the days you are not. But then you can see how it plays really nice, the adaptive lighting control. The days that you are not achieving your target DLI by the sun, the adaptive lighting control will push the hard light, trying to get to the target. But the days that you are above, you really minimize the energy consumption, saving energy. And that you can compare with the simple threshold control, where you're going to have a monthly cost for this scenario of $7,000 versus $4,300 with the adaptive lighting control. And again, the timer here to the left, just to give a good comparison of what happened with no controls at all. Going to the next month, then gets really interesting again. That's what I would call the peak of the winter. And if you're in the more northern latitudes, I'm on upstate New York, we have more days like that than in Las Cruces, New Mexico, or Tucson. Here is where we have most of the days not reaching the target DLI. And here, the technologies tend to be similar as well, the adaptive lighting control and the threshold, because in this case, you're pushing your lighting system harder to get to the target. So if you just don't have enough supplemental, enough natural sunlight, you're going to push hard to try to get your target. So you see that the savings are not very high. But as you move forward, and now we are in February, you get your similar situation again, where you have enough light coming from the sun. The reason you have a big difference in the energy consumption is because with the adaptive lighting control system, it realizes you're constantly recalculating, and you very early in the day, you stop to provide supplemental lighting versus the threshold control. You keep pushing until the light does not pass the threshold of 300 micromoles. A point to make that the reason we still see supplemental lighting, even with the adaptive lighting controller being provided every day, is because very early in the day, so if you think between 6 a.m. to about 9 a.m., there is just not enough sunlight in the sky. So the dimming functionality, just the adaptive lighting control, will not account for that. But we're going to take a look later on other methods you can use to fix that. Just a point to be made here. Now what I'm doing, I'm running the similar scenario. Everything is the same, but now we are changing the lighting capacity to 110 micromoles instead of the 210. And you can see that overall, the cost is going to be lower, but you're going to achieve your target DLI less days of the year as well. The big change here, the reason growers would do that is really related to how much the delta you are trying to make up, which is the delta from what is the target DLI that you're trying to achieve versus what you can get in the darkest months of the year versus the cost of implementation. I'm not going to go into the costs of the supplemental lighting system itself. It's not the point here. It's more about the lighting control, but that's what people have to keep in mind. And that's what growers keep in mind when they're making those decisions. Running now with 110 micromoles, we can see similar situation early in the year, well, late in the year, but early in the lighting season when it's November. So most of the days you're getting to your target DLI. As you start to go to the shoulder months, because again, now you have a lower capacity, they tend to even out because you're going to be pushing, both systems going to be pushing to the maximum, and they're not always going to reach the target DLI. It's just not enough supplemental lighting for the shoulder months. However, when you get to the very darkest months, then they tend to even out again. You're just pushing to the maximum and you're not getting there. So here you can see it's even closer, the energy consumption between the adaptive lighting control, more advanced, and the simple threshold. And as you go back again to the shoulder month, which here is almost done the shoulder month, so you don't need supplemental lighting again, you see the biggest benefits early in the day because the adaptive lighting control is calculating. The variable thresholds are telling to use less energy than just the fixed threshold, the case in the middle. A quick summary at the end. So what I did, I took these two scenarios and I just put them together so you can have a better overall comparison here. So again, Las Cruces from November 2014 to February 2015, so 4 months total. The adaptive lighting control under the 110 micromoles capacity would use $9,250. The simple threshold control would cost the grower $12,700, and if they run just on timer, more than $30,000. The savings calculated just below. The first line compares the savings of these two technologies, adaptive control and threshold, to the timer, so we can get a lot of savings if we're not using, I would even say not using a control at all, considering the timer too basic. So you can get $22,000 from the adaptive lighting control and $18,000 with the threshold. And if you compare the adaptive lighting control through the threshold control, then you get an extra savings of $3,500 just by using the adaptive lighting control. That's under the 110 micromoles. If you now move to the scenario where we have a more powerful supplemental lighting system with 210 micromoles, your energy savings is going to be bigger because everything being the same, when you go to the shoulder months, you're going to be saving more energy with the adaptive lighting control than you would with the threshold control. So then you get a bigger savings here of almost $10,000 by using this more advanced technology. Other things we can do with adaptive, not adaptive, but advanced lighting controls, and those are some of the things that some people are using in the industry, but most of them are not, and they're actually pretty simple. Photo period, just by adjusting the time of the day that we're going to start your supplemental lighting and when you're going to finish. So not really changing the photo period, but just shifting the photo period to later in the day so you can take more advantage when the sun is up, and you can avoid that extra energy that we saw at the beginning, even when you had very sunny days. I have one example for that. Daylight extension, we could and we should take advantage of the LEDs being dimmable fixtures. If you're going to work with daylight extension, you can keep the lights on at a fraction of the power. And that's something we are already implementing. You can keep the lights at 10% of the power, for example. If you achieve your DLI before the photo period, you keep them at 10% of the power, you're going to get to the same photo period. You're going to be consistent for the plants. You get that daylight extension that you need, but at a fraction of the cost of the energy. The threshold control, that's something that can be used can be complementary and can be used in addition to the adaptive lighting control, meaning that you can impose a cap no matter what the adaptive lighting control is telling you to do, recalculating the thresholds. If you have a very high target DLI, for example, with cannabis crop or hemp crops, where they're shooting for a DLI of 40, 35, up to 50, sometimes the system will tell for supplemental lighting to be used even when it's midday and you have already 2,500 micromoles from the sun. That's not a good use of energy, electricity energy for lighting. The plants cannot use the light really well at those levels. So you can impose threshold control to put caps and maximize the energy savings. Same thing for the night interruption. If you have LEDs, you can, and you're controlling flowering, for example, you can come up with the night interruption at a fraction of the energy. The DLI carryover, it's a very nice new feature that we are offering now, in which if you have excess of light in one day, you can carry the excess. So let's say your target DLI is 17 and you achieve 18 or 19 or 20, you can carry some of that to the next day. That's a very new technology recently published at the University of Georgia, which is being implemented, and growers are really liking that. And then zoning is just impressive as well. The amount of variability that you find in commercial greenhouses nowadays, same greenhouse with multiple lighting systems, or same greenhouses with different zones, different applications, just by zoning them and allowing growers to control them separately can provide big energy savings. Here I provided just a quick example with that shift of photo period. I'm not going to take examples on the other ones. We don't have time to go through all of those, but that's a simple example. We run the same simulator for location here in upstate New York in Geneva. I took the year of the month March 16, 2016. Target DLI was 18 moles per day. A system with similar light intensity that we saw, 110 micromoles at crop level, crop canopy level. The photo period is variable. That's what we're looking right now. But just using a small canopy area just to demonstrate, and a 10 cents energy rate. If you keep your lights on starting at 3 a.m. and running all the way to 5 p.m., under those setups, you would be spending $277 with the adaptive lighting control. And keep in mind, that's a much lower number here because they have a much lower area as well. That's just for demonstration. Now, if you take the same photo period, but if you shift for later in the day, you can get an energy savings of 40% just by doing that. It might sound very obvious, and you say, well, why people are not doing this already? One of the reasons, and a specific reason in this case, is because this grower has troubles with his neighbors with lighting pollution. 5 p.m. in upstate New York can be dark already during the winter. So just to keep in mind, there are other reasons involved, but there are other solutions involved. But I just would like to make the point that sometimes people just don't consider these very simple measures, which can be very, very cost effective. Now, I will switch gears to a project that was actually implemented in upstate New York. That's a partner of ours, Whitfield Gardens, was a project sponsored by the Department of Energy here. And I'm going to show now a little bit of the challenges of implementing those technologies. That was the point of my talk. Advanced lighting controls, what can be done, how can we implement into the industry, and the difficulties that we have to get those technologies that we know will work, getting into every greenhouse everywhere. In this case, we work with Field Gardens. They are in North Tonawanda, so it's Buffalo, close to the Buffalo area. They have deep water culture pounds of lettuce. They are targeting a daily light integral of 18 moles per meter square per day, and we run this experiment from January to May 2020. So it was this threshold control versus the adaptive lighting control system. Under the adaptive lighting control system, our target was 18 moles of light per meter square per day. And while with the threshold control, they didn't have the DLI control, was just turning the lights on and off at 500 micromoles light intensity at the canopy level. All the rest the same. Let's take a look on what it does to the crop and how much energy savings you can get. This is a nice picture, aerial picture from that facility. So that is the test bed we were working with. Few interesting things to highlight what we saw on the theory and how we can apply in the real world. So I'm just dissecting the data analysis starting from December to January. We don't have the complete data set here because that I took from this specific project where the grower was feeding us data back. So I have the chops of data that I could put together for this presentation. But here is what the data looks like from December to January. And I would like to show at the beginning, we're going to look later in the year as well. But my point here is that being in Buffalo or upstate New York, throughout the entire period from December 11 all the way to January 17, just not enough light. Very, very minimum amount of light coming from the sun. So the sunlight contribution is the blue part of the bars down here. And you see, well, I have on the slide going into the details. And then the supplemental lighting coming from the LEDs working at full power every day, and you just don't get close to your time. The graphic below shows just the LED, so how much LED, the supplemental lighting LED system was used compared to the maximum capacity, which is pretty much if you're running them at full power the entire photo period. That's just to understand these graphics. Now we're going to take a close look at them. So during this period from December to January, the sun contribution got an average of 3 moles per day, 3 moles per meter square per day. LED contribution, the maximum capacity was 5.9 moles per meter square per day. The average was also 5.9 moles per meter square per day. So pretty much running the entire time. And the target DLI, which we were trying to get to 18 moles per meter square per day, maximum we could get was 12.2 and an average of 9 moles per meter square per day. If you look at the supplemental lighting system, just being fully used every day. Now I'm taking data from December to March. So it's the same graphic, but now extended. It's pretty interesting to see that here, when you get to February 15, you start to get more consistent sunlight levels. And now the adaptive lighting control really starts to kick in and you can start to save energy. That's a close look. Now just the usage of the supplemental LED lighting system. You see that from February 15, we don't use them to full capacity anymore. And that's when you can see the shoulder months that you saw on the simulator kicking in here. And now we're going to take a look each one of these months, what happened and the modifications that you can make working with a commercial grower to achieve even more savings, taking the full advantage of advanced lighting systems. So in January, the lighting systems was utilized at full capacity, trying to achieve the target DLI. So here we're really prioritizing consistency and getting the crop growing. As you go through February, you start to see the dimming capability kicking a few days of the month, so 8 days of the entire month. That's what we're looking here into those graphics. Target DLI of 18 with the green line, gray parts of the bar, sunlight, and the purple, the supplemental coming from the LEDs. And the graphic below here, you see a supplemental lighting system that is never turned off, sorry. It just stays on for the entire photo period. And the purple line is the adaptive lighting system going up and down. As you go to March, you start to get even more savings. Here, when we provided the recommendation for the grower to go from 3 a.m. To 6:30 p.m., moving this photo period to 4 a.m. to 7:30 p.m. So here we start to save energy on the days that you are going above the target. And this is mainly saving energy early in the day when the system doesn't know how much light you're going to get from the sun. As you go to April, we start to notice that you're getting more consistently sunlight achieving the target DLI or getting close to the target DLI in conjunction with the supplemental lighting. So the recommendation was to turn the supplemental lighting down to 50% from 4 a.m. to 9 a.m. when you don't know how much light is going to come from the sun again, but the crops are growing well. So the grower decide to make this change to prioritize energy savings. And as you go to May, you save energy pretty much every day of the month just with the dimming technology. And you can see, again, at the bottom part of the graphic here, how the supplemental lighting is being used compared to a non-control lighting system. Showing at the bottom right, that's the year to date, so the cumulative savings. The purple part of the bar graphic is how much light was used by the supplemental lighting system, and the green area shows the energy savings. And that's natural, right? From any lighting system pretty much. As you go from the dark months to the shoulder and more bright months, use less light, and you get more energy savings. That's a nice picture early in the day. So it gives a nice idea again, even though you come in the sun, a lot of energy that you can be using. So if you can nail down this energy consumption early in the day, you see by the intensity of the lighting, you can achieve good energy savings. This is a summary of the overall project. So at the end of the trial, they saved 33%, they achieved 23% in energy savings, which is the equivalent of $20,000, $25,000 per acre, and 200,000 kilowatt hours per acre. The ROI calculations, we don't have to go through the numbers. It's just to show the annual savings on an acre base, again, $25,000. And here we pretty much normalize for the annual savings. We normalize from January to May. We expand as if they were starting now in September all the way through. Now, why is so hard to implement those technologies in like many greenhouses? We saw the theory, we saw the applied technology. You can achieve the energy savings. Those are technologies that are readily available. Cornell University has the GLASE system, for example, developed years ago. It's ready to go. Why is so hard? Altogether, on my roles with Candidus and the GLASE, the Greenhouse Lighting and Systems Engineering Consortium, we have secured 28 paid trials for growers to implement those advanced lighting controls. And I'm not talking about the company, I'm talking about in general, LASI, all kinds of advanced lighting controls. We got grants from the USDA and RCS, USDA specialty crop log grants, utility companies, PG&E in California, Georgia Power, NYSERD in New York. All of those trials, we are successful finding people, but it's very hard to find participants. And that's because there's a big gap into what we can do in the research, what we show that can be done, but for people to really implement those technologies. And that's what I'd like to talk a little bit now and really open for questions in the conversation on how can we bridge those gaps. One example is the GLASE, work we do at the GLASE consortium. Things I've seen over my past 4 years in this role is that these public-private relations and partnerships are very helpful. We have to demystify those technologies. We have to break the skepticism. We have to de-risk these technologies in the eyes of the growers. So not only showing that it works at a bench, right, at the laboratory or at the research greenhouse, but at a commercial facility. So working in partnership with the industry is very important. And I think I'm sure that's something that CEAC does really well as well, is bringing all these stakeholders together through the short courses and all the events that you do to really bridge this gap, not only the educational content, but the demonstration as well. One thing we think works really well with GLASE is the technology de-risking process. So we involve all these stakeholders at the beginning, from the technology development, going through the proof of concept, technology validation, we do pilot implementation in commercial greenhouses, and then we push for the industry adoption with a whole educational package around that. So that has been very helpful to move some of those technologies that are developed into the academia, into the commercial world. Another thing that is picking up now, I think here is also, is at the same time the cause and the solution. The cause is the lack of regulatory policies and standards with the greenhouse industry, especially if you think about lighting. It has been a mess up to now. I think now the organizations are getting together, they're getting word about that. I think we have a very long way to go. We're still developing, right? We're still redefining terms, we're still defining standards, but this conversation has started, and I think that has been very helpful to the industry as well. I just listed a few initiatives that you see state level, and as you can see here, those are all states with relevant cannabis industry. Although we don't work with cannabis at the GLASE consortium directly, that's not one of the crops that we do experiments. We do have members that work directly with them and cultivators. But I think overall the lesson here is that the cannabis industry is really pushing for some of those regulatory policies and standards, which is at the same time good and bad. So just a few examples. California with the Title 24, where they're putting new standards for the energy consumption and efficacy of lighting systems. Massachusetts, they have the Cannabis Control Commission. Colorado, through the Department of Public Health and Environment, they constantly put RFPs, and that's another great opportunity to work with the industry in validate and demonstrate the benefits of energy efficient technologies. And Illinois also has adopted some of those standards. Another point I would like to make on the difficulty of pushing new technologies to market, new emerging technologies, I would say, greenhouses are very different, right? So I have different facilities in different locations, growing different crops with different technologies. As you can see here, there are 3 types of lighting systems, right? I'm just highlighting one type of LEDs, lighting system. So I have some top lights, non-dimmable. Then you have another technology here, which is dimmable LEDs, which is a different control system and offer different benefits, and just traditional HPS lights. The point I want to make, and the reason I took these 3 specific pictures to show how the industry varies, is that these 3 pictures were taken at the same facility. So that's the same grower, right? They have these different stages, different lights, Crops might respond very differently to them. So within the facilities, you already have this high variability. If you think about across facilities, across crops, across states, it's really hard. So every time you have to prove the value of technology to one area, and then you prove in another one, and then another one. And it takes time to work with the growers so they can get the trust and really make this change and adoption to the new technologies. Just another point to make here on this picture is that I took these 3 pictures facing those crops, but behind me on those pictures, there were 3 different control panels. So not only the technologies are different, but the way you control them are different, right? From the electrical panel to the climate control system controlling those lights. So huge variability in the industry. The last point I want to make on this presentation, so we've gone through benefits that the technology can offer, a case study, the challenges, and I think just to conclude here, areas that I see of potential research to continue to be developed and help to push those technologies is variable price of energy. Over the past 2 years, I would say, there has been a big wave of programs pushing greenhouses and indoor farms, so CEA facilities in general, to take advantage of variable price of energy. That's a big push coming from the utility companies. They say those are utility incentive programs, but many times they can be punitive programs, meaning that if you use energy during peak hours, not only you're paying a high price, so here's October through May in Michigan, you see that during this period, if you use energy from 4 p.m. to 6 p.m., you're paying about 8.9 cents versus 7.3 through other hours of the day. So not only the price is higher, but also there is a penalty just for being using for use energy at this time of the day. So you can see taking advantage of avoiding energy use during peak hours, but also not being punished by using during these hours. Programs that are trying to push limit the amount of energy from the lighting systems during the certain hours of the day, or just avoiding at all. There is a big push from them, but a lot of reluctance from the growers. And I understand there is many questions to be answered before go and implement this at a commercial level. Just to make another point that those variable price of energy, the variance in price is even higher during the summer. So maybe not a good deal for lighting. You're not going to be using lighting here, but for indoor farms and any other cooling systems in commercial greenhouses, that could be a big advantage there to be taken as well. To conclude my talk and open for questions and discussion, I just would like to mention that coming up October 14 through November 18, we are releasing the 2021 Virtual Plant Lighting Short Course, in which you're going to be covering all aspects related to crop lighting. As you can see here, there are 6 modules from Introduction to Crop Lighting all the way to the Future of Crop Lighting, in which we're going to be hearing from Dr. Kasira on module number 6. I'm really excited with that. So just open the invitation to everyone. If you're interested in learning more about, that's a fantastic opportunity open to everyone. You can take a look online or just reach out to me afterwards. With that, I conclude my talk and just say thank you again for everyone for participating and listening to this conversation.